Hello, this is Ms. DB, and in this lesson we are going to go over geometric probability. This is the last section in Chapter 9, Chapter 9, Section 6. And we're just going to calculate geometric probabilities. There's a little bit of review about what probability is, and it is the set of all possible outcomes. Well, probability is when the outcome you desired, you take it out of the possible outcomes. So the sample space is the possible outcomes you could have, and the outcomes, any set of outcomes, is called an event. So what you do to find the probability is you take the number of outcomes in the event out of the total number of outcomes in the sample space, so the total possible. That's the theoretical probability. Like if you want the theoretical probability of rolling the number 1 on a dice, on a number cube, it would be 1 out of 6, because the number of outcomes you want is 1, and the number of outcomes in the sample space is 6, because there's 6 sides on a cube. We're going to use this with geometric probability. In geometric probability, it's when you have a figure that you're trying to find the probability of. So it's usually going to be a geometric measure like area or length, and the outcomes are going to be like points on the segment or points on the figure. So picture it like this. Let's say we have this rectangle over here, and I want to know what is the probability that if I have that figure laying down on the floor and I drop a button. If I drop a button onto that figure, what is the probability that it will land in the shaded region, the region of the rectangle? So if I could find the area of the rectangle, then that would be my event, that would be my desired outcome, and the total outcome would be the area of the rectangle. So you have to find two areas and then write it as a ratio. If you're looking, like this is usually a spinner kind of problem, like if you spin the spinner, what's the probability it'll land in this region, this sector? You need to know what this angle is here. And then there's 360 degrees in a circle, so you would take the measure of the angle, let's say that's 50 over 360, that would be your probability. The segment ones are really the easiest ones. You are going to find the length of the piece that they say, what if you drop it in, what's the probability it'll land on segment BC? You would take the length of that over the length of the whole line segment. So in this case, BC over AD. Every once in a while, they'll say, what's the probability that it won't land on that? And then it can be easier. The event not occurring will be 1 minus whatever the probability of that occurring would be. Sometimes it's easier to find it that way. All right, so here's our first example. A point is chosen randomly on PS. So this is my whole segment here, PS. They want to find the probability that the point will land up on RS, which is just this little piece. So you take the little piece of 5 over the whole segment. Well, you have to add up to get that. 7 plus 13 is 20 plus 5, 25. And then simplify that. Now you can write probabilities. Probabilities will be between 0 and 1 if you write them as fractions or decimals, or between 0 and 100% if you write it as a percentage. This is the same as 0.2, which is the same as 20%. Sometimes the problems will ask you to leave it in a fraction form or a percent form. If they don't, you can leave it in either one of these three forms. All right, so the point is not on QR. Okay, let's see. If it's not on QR, it must be either here or here. So we have two ways to do this. We could take 7 plus 5 is 12 over the whole thing is 25. This is the same as the length before. 7 plus 13 is 20 plus 5. So we could say it's that, or we could say that it's 1 minus QR is 13/25. And that's the same as 25/25. 1 is the same as 25/25 minus 13/25, which is 12 over 25. So you get the same answer either way. There's just two different ways that you can solve that. This one says the point is on PQ or QR. Here's PQ, here's QR. So we could say, okay, well 7/25 plus 13/25 is equal to 20/25. Or we could add them together first. 7 plus 13 is 20, and say it's 20/25 from there. So again, there's more than one way to solve this. Once you get your 20 over 25, you should simplify that fraction. Both of these are divisible by 5, and that's where they get the 4/5 as their answer. This is just another example. You should try this one, pause the video, check your answer, and then you can move on to the next section. All right, for this one you should have gotten that you would get 8 out of 12, but then simplify that to 2/3. All right, this is an application to what we just worked on. A pedestrian signal at a crosswalk has the following cycle: walk for 45, don't walk for 70. What is the probability the signal will show walk when you arrive? So you could draw a segment to show the 45 and the 70. So here's our 45, here's our 70. So the whole segment is 45 plus 70, or 115. The probability that it will be on walk would be the 45, because this is our walk, and this is our don't walk. And then you would take your 45 over 115 and simplify it to its lowest terms. And you could leave it like this, or they change it, this time they change it to a decimal. This one is saying that if you do this 40 times, predict about how many times you will have to stop and wait for more than 40 seconds. So if we go back here to this one, we can see that it's every one cycle is 115 seconds. And they're asking, what is the probability you have to stop and wait more than 30 seconds? 40 seconds. Is represented by a segment that starts at B and ends 40 units away from C. So the whole thing is 115. And they're saying this is 40. So 115 minus 40 and what was this, 45 here? 45. Okay, so here's our don't walk. Here's our walk. And then in the don't walk, they're breaking that up into 30 and 40. The probability of stopping and waiting more than 40 seconds is 30 out of 115. Because if you land here, then you don't have to wait. If you land here, you don't have to wait more than 40 seconds. So it's only if you arrive right here that you would have to wait for more than 40 seconds. So it's 30 over 115, which simplifies to 6/23. Now you can just multiply that by 40, and you would get about 10 times. That's rounded, but that would be approximately how many times you would have to stop and wait more than 40 seconds. All right, let's go to some spinner kind of questions. It says, what is the probability that the pointer will land on yellow? We can see that this sector here is 140 degrees. Every single circle is made up of 360 degrees total. So we would take the degrees in that yellow, in the event that you're trying to find the probability of, over 360, and then simplify. If we want to do the same problem, but this time landing on blue or red, we have to add those two probabilities together. So 52 plus 60 is 112, and then you take that out of 360 and simplify. Always simplify. This one says the probability of it not landing on green. It's easier to take 1 minus, or 360 over 360 minus the 108 over 360. So you would get 360 minus 108 is 252. That means all of these angle measures together equal 252. So 252 over 360, then of course simplify, you get 7/10. This is a different spinner. Use the spinner below to find the probability that the pointer will land on red or yellow. If it's red or yellow, you would add those two together, 180, divide by 360, that's 1/2. All right, now we're going to use area to find geometric probability. So here is kind of this complex figure. We want to find the probability that a point chosen randomly inside that rectangle is in each shape, and then round to the nearest hundredth. So the first shape is the circle. So here's our circle in here. It's got a radius of 9, because I know that because the diameter is 18. Area of a circle is pi r squared. So we plug that into the formula and get 81 pi, or about 254.5. So the area inside that circle is about 254.5. Now we need to find the area of that whole rectangle, which is base times height, or 50 times 28. That's equal to 1,400 feet squared, and then the probability that the point at random will lie inside the circle is this number, 254.5, over 1,400, and then you can get a decimal approximation that this probability is about 0.18. Now we can use the same picture and find the probability that a point chosen at random will lie somewhere else. The trapezoid. Now we would expect it to be bigger than 0.18 because the trapezoid is taking up more space. The area of a trapezoid is area equals 1/2 base 1 plus base 2 times the height. We plug in the parts we know. Base 1 is 34, base 2 is 16, the height is 18. That's 450. Now we already found the area of the rectangle. We wouldn't have to find it again, but in case you forgot, it was 1,400. So our probability is going to be 450 over 1,400, which simplifies to about 0.32. So it is a higher probability that a point chosen at random would lie inside that trapezoid. Okay, well, let's find the probability that it will lie in either of the two squares. The area of the two squares, we could just find one of them and multiply it by 2. And one side of the square is 10, so 10 squared is 100, and there's two of them, so 200 square feet for the squares. Now we already know that the area of the rectangle is 1,400, so we just take 200 over 1,400 to get the probability that a point chosen at random would lie inside either of the two squares would be approximately 0.14. Now what if we said not in either of the two squares? Well, we just found that the two squares is equal to 200 square feet. And we know that there's 1,400 square feet in the whole rectangle. So if I subtract, the probability that it will land somewhere besides in those two squares would be 1,200 over 1,400, which simplifies to 6/7, or you can change that to a decimal. So the likelihood that it would land somewhere else is pretty good. 6/7 is equal to about 0.857 as a decimal. All right, so here's a problem for you to solve, and then you can check your answers. Pause the video and try this one on your own paper. All right, this says to find the probability that a point chosen randomly inside the rectangle is not inside the triangle, circle, or trapezoid. So one thing to notice is that the circle is already inside the triangle. So you really only have to find the area of the triangle area, and the area of the trapezoid. And if you find both of those and subtract it from the area of the rectangle, then you'll be on track here. So the area of the rectangle is 20 times 45, or 900. And this answer they got for the triangle and the trapezoid is 0.29. So you might, let's see, this radius is 6. Doesn't matter. I'm trying to find the dimensions of the triangle. But all they're giving me is the radius of the circle. If this is 6, how does that help me find the area of the triangle? The trapezoid, they give me everything I need. 1/2 base times height, or the bases added together, and then half of that times the height. But what about this triangle? I don't know. I don't know that I know this. It is an equilateral triangle. Does that help us? This would be 6. Oh, this is 6. But that's not the whole height. So all the radii are 6, but I'm just saying, well, how does that help us find the height or the base of this triangle? It's a 30, 60, 90 triangle. Here to here is 6. I don't know this dimension though. I don't know. I would need more information. There won't be one that hard on your worksheet. All right, so good luck. Let me know if you have any questions, and I will help you out. Thanks a lot.